Find the maximum steel ratio in a singly reinforced concrete beam as a function of beta, F prime C, and Fy. In this equation, beta is a constant which depends solely on F prime C. F prime C equals the compressive strength of the concrete, and Fy equals the yield stress in the steel. In this problem, we are given that the minimum strain in the steel, epsilon s, is 0.004. This is a typical design requirement to ensure the tension steel in a beam yields. The equation for the steel ratio in a beam is the area of tension steel, AS, divided by the quantity, the width of the beam, B, times the depth to steel, D. For this equation, we'll solve the area of steel term, AS. From axial force equilibrium, we know the tensile force in the steel, TS, equals the compressive force in the concrete, CC. More specifically, the area of steel times the stress in the steel equals 0.85 times F prime C times A times B. Next, we'll isolate the area of steel term, AS. Since we're assuming there is sufficient strain in the steel to cause the steel to yield, we can substitute the yield stress of steel in for the stress of steel in our equation for the area of steel. Next, we'll solve for the variable A, where A equals beta times C. And we can solve for C using strain compatibility and similar triangles. After a few lines of algebra, we find that C equals the strain in the concrete times the depth of steel, divided by the strain in the concrete plus the strain in the steel. Since the problem asks to find the maximum steel ratio, this means we'll want to maximize the area of steel, AS, and since the area of steel is inversely proportional to the strain in the steel, epsilon s, maximizing the area of steel means minimizing the strain in the steel. Therefore, we'll set the strain in the steel to its minimum value of 0.004. Next, we'll set the strain in the concrete equal to 0.003, which is a typical value for concrete crushing in concrete design. Now we'll return to our equation for the length C. Plug in the strain values for the tension steel and compression concrete, which makes C equal to 0.429 times D. Now we can plug this value of C into our equation for A, which makes the area of steel equal to a function of beta, F prime C, and Fy. If we substitute this value for the area of steel in to find the steel ratio, we notice that the terms for the beam width, B, and the depth to steel, D, cancel out of the equation, and the maximum steel ratio equals 0.365 times F prime C times beta divided by Fy. When reviewing the possible solutions, the answer is B.